All right, hey, welcome back. We're going to look at another problem from the fluids unit for Physics 2. This problem has to do with, of course, fluids and, in this case, buoyancy. But not only that, I think it can be applied to a lot of different areas of physics. So let's take a look at it. I'll read it out to you. Question says, a block is submerged in a container of fluid. Which of the following describes the microscopic cause of the force that the fluid exerts on the block? Okay, so let's just draw a picture. I know. So this is force the fluid exerts on the block. So here's our liquid. It's submerged. Here's our block. Maybe it's sitting on the bottom. I'm just drawing it in the middle. But we do know that there are forces acting on all sides of this block. And we'll talk about how they balance out. But that's the pressure. That's the liquid's pressure on the block, right? And that pressure surrounding the block is what causes the buoyant force. But they're asking, what is the actual cause of that force? I mean, pressure is the cause, but what is the microscopic cause? So let's think about this a little bit. We know that fluids are made up of molecules. Everything is, right? And those molecules in a fluid are able to move around freely, and they're flying around, and they have some average kinetic energy based on their temperature, right? And I think a lot of people's first instinct, they know that water pressure, it's caused by collisions of those molecules with the block, okay? But when we read through the options here, collisions isn't mentioned anywhere. So those collisions are happening, yes, but we need to look a little bit deeper and a little bit more detail in what that collision actually is. And it's kind of interesting. It's a little different way of thinking about applying forces on things. When we touch things, when I push down on this paper, right? My pencil is sitting here and I push it. What's the microscopic cause of my finger being able to put a force on this pencil? That's what we're going to get to the bottom of right now. Let's read the options here and just think them through, and then we'll talk about this microscopic cause of that force on the block. So the first thing they say is maybe it's the gravitational force between the molecules of the block and the molecules of the liquid. Maybe, I guess that's possible. Let's pretend that that's a real choice, like that's a viable choice. If that was the case, then every molecule on the edge and every molecule in the block would feel the same force, and that would be an attractive force, right? So if we had another situation, let's think of a sphere in a liquid, right? We know that this should have any submerged object, maybe I'll draw it in green, has some buoyant force, right? But in this case, if there was this gravitational attraction, right? So maybe there's a molecule up here and a molecule in here, and there's a little gravity up, well, would that be able to account for this buoyant force? Well, at the bottom, there'd be a similar gravitational attraction down, and each side would be pulling. And I mean, if we summed up every single one of these, there'd be a lot, but they'd all be exactly equal, and they'd all cancel each other out. And in this case, if that was caused by a gravitational attraction, that net force would equal 0, and that's not what we see. We see a net force up, right? That's what our buoyant force is. It's a net force in the upward direction. So it doesn't seem like that's the case, okay? Doesn't seem like it's gravity, right? And that collision, we want to go back to that collision idea. You wouldn't say that when I collide with the pencil, when my finger collides with the pencil, that's not a gravitational, I'm not attracting the pencil to my finger, right? So that really doesn't add up in two ways. So let's say no way on choice A. Now B, C, and D all talk about electrostatic force. Now you might think, weird, why is electricity coming into this? We're just talking about fluids, and we're talking about what's going on in these liquids. And buoyant forces, right? No electricity, no charges here. But we remember molecules are made up of atoms, which have nuclei that are positive, and electrons flying around those nuclei. So we do have some charges inside these molecules. So if we read our options. B says it's an electrostatic force between the electrons in the molecules of the block and the electrons in the molecules of the fluid. So that, let's write our options. This is B, choice B. It's electrostatic, but it's electron to electron. And I'll say this is my block, and there's a little raindrop for my fluid. Okay. So they're saying maybe it's electrostatic force, electron to electron in the block to the fluid. Choice C is electrostatic force between the nuclei in the molecules of the block and the electrons in the molecules of the fluid. So this case, we're saying a nuclei, I'm going to put N for nuclei, and electrons in the fluid. And D, electrostatic force between the nuclei in the molecules of the block and the nuclei in the molecules of the fluid. Now, let's think about this. Now, a collision, right? We were just saying this before. A collision between these molecules. When I say my finger collides with a pencil, it's not really an attractive force, right? So this would be an attractive force, right? Our nucleus is positive and our electrons is negative. That would create some sort of an attraction between them. And that's not really what we think of when we think of a collision. Collisions, we think they hit into each other and push in the opposite direction. So probably not this one. Let's go through and just double check, and let's think about B and D. Now, these are talking about a repulsive force. They're pushing away. Electrons push other electrons away. The protons in the nuclei, right, because the nuclei are positive from the protons, they repel each other also. Now, I'm not drawing this to scale in any way, but if I put like N here for nucleus, and I'll put a big positive here, right? This is our nucleus, and we have all of our electrons flying around in their orbitals, right? Simple diagram of our atom, right? We know that's not exactly what it really looks like, but for our purposes, it's a pretty good picture. And then we have nucleus over here and other electrons flying around. Well, if this was our block, this is our liquid, we're kind of, in most cases, unless it's an electrostatic problem and they're telling us charges on things, we're thinking block's probably neutral. The liquid's probably neutral. So that means that however many electrons are flying around in the water, there's probably an equal number of positive charges, protons, in the nuclei of the molecules of the liquid, right? And the same thing over here in our block. If it's neutral, the number of electrons supplying our negative charges is equal to the number of protons in our nuclei of our molecules. So this is totally neutral and totally neutral. So what do we notice? Well, when this guy flies around, at some point, the electrons are much, much closer together than these protons would be inside the nucleus, right? And if the amount of charge that we're talking about, right, let's say this charge and this charge are equal charges, well, the repulsive force here, let's draw them, between the electrons, this is going to be a big, much bigger repulsive force than what we feel because of these positive charges. Okay? So the best answer here is that force that the block feels from the liquid is due to the electrostatic repulsion. It doesn't say that, but it's the repulsion of the electrons around the molecules of the block and the electrons around the molecules of the liquid. All right? So, like I said, yeah, we're talking about liquids, but this is true for all contact forces, right? So, you know, if I want to apply a force to this pencil, I push on it, That was because the electrons in the molecules of my finger repelled the electrons in the molecules of the wood, right? It's a different way to think about contact. When we start learning about this, sometimes we say you can never actually touch something, right? Because these electrons repel the two objects before they can ever actually, quote unquote, touch. So, different way to think about forces. Hope it helped, and see you on the next video. Take care.